Talk tangent line approximation to functions from the complex numbers to the complex numbers. So our tangent line approximation theorem looks something like this. It's an equivalence to differentiability. Basically, it says if a function is differentiable, then you may approximate it very well by a linear function, at least nearby that point where it is differentiable. So let's take a close look. We have a function defined on an open subset of C. Really, I just mean that it's defined on a neighborhood of a point. And we have a point in that open subset. Then the derivative exists if and only if we get these other conditions. And these other conditions are really guaranteeing us that there is a tangent line approximation. The tangent line approximation is the function L, and the function G, well, we'll talk in just a second about what that is about. So let's draw in the tangent line approximation to our function. Now, as I begin using this picture, I want to caution you that this picture is a little bit of a lie. This is a function f from u to c, and u is an open subset of c. And I've plotted u horizontally here as if it is a subset of the real numbers, and I've plotted c vertically as a mere line, as if it is just the real numbers. This picture is a bit of a lie. This is the correct picture if the function f has a domain of R and a range of R, which is not actually the situation here. Why did I draw this picture instead of the right picture? The right picture is four-dimensional. And so this picture gives us a pretty decent intuition about what's going on with the tangent line approximation, and it fits on the whiteboard. So there is a little bit of a lie in this picture, but in a lot of the cases, the lack of dimensionality of this picture is not really the point and doesn't really deceive us very much. But I just want you to know that this is not really faithful to the true setup here. So the tangent line approximation theorem says that f is approximately L. But to say the two functions are approximately equal and to not say anything about that approximation is kind of useless. So instead of saying simply that if f is approximately L, we say that f is L plus some other function g, and g is the error function. Well, by itself, that doesn't really mean anything. I could subtract any linear function from f and I could get a function g. I have to say furthermore what we know about g. G is not a very big function, right? In this graph, this function that I've plotted in blue is L, and the function g is the space between the graphs. It's the function that if you subtract these, it would kind of look like this. So g would have a graph like that. So g is the error function and L is the linear approximation. Now, what do we know about the error function? If the approximation is any good at all, then the error should be small. And in particular, the error should be 0 at the point of interest. And so we get the further condition that g of z is equal to 0. That basically says that the error function does not have a significant error at that individual point. And then we need something else about the error function. It can't be the kind of function which takes very large values, and then just drops down to 0 at the point of interest. It has to also approach 0 as we approach the point of interest. And so we get this condition that the limit of g of z as w approaches z is 0. Now, that's going to be true about the linear approximation, but it's actually not enough. The problem with this condition is that it doesn't account for the fact that any other linear function would differ by a function that also approaches 0. So let me draw in a hypothetical here. Supposing in orange here, supposing this were what we used as the linear approximation. Now, if you're looking at this and thinking calculus, you're probably going to recognize that doesn't look right. That doesn't look like the linear approximation at all. It has totally the wrong slope. It's not a very good approximation to the function at all. Nevertheless, if we subtract the difference between the original function f and this new bad approximation in orange, well, we will get this difference. And this difference also approaches 0 as we allow w to approach z. So even a terrible linear approximation, which isn't the right one at all, would have this condition that the error function would approach 0 on both sides. We would get a limit of 0. And so this limit function requirement on the error function g is not actually strong enough. What we need is a modified requirement, and let me fill that in. So g of w over w minus z has a limit of 0. So let me explain what this is really saying. As w approaches z, w minus z approaches 0. And as w approaches z, g of w approaches 0. And when we compare the ratios between them, this requirement says that that ratio goes to 0. In other words, it says that g of w not only approaches 0, it approaches 0 faster than the function w minus z. And so here, what you should sort of take from that in this example is that g of z is more like a quadratic function than it is like a linear function approaching 0, right? It's more like a function like w minus z quantity squared, which is approaching 0 faster than the function w minus z. This thing, this difference between the original in black and the orange here, it will approach 0, but not appreciably faster than w minus z. And so this stronger condition, g of z over w minus z approaches 0, actually is the right condition that we need in order to say that the error function g is really doing a good job being the error function. So the purpose of this is that it allows us in some situations to replace a function f with a linear function, which has the same properties. At least the first derivative is going to be the same. So you might think, I mean, the statement of this is kind of fancy, and we've had to reason very carefully about the reasoning about which things approach 0 and how fast. You might think that the proof is rather sophisticated. The proof is actually dead simple. You can fall accidentally into the proof of this just by manipulating the definition of the derivative. So let me give a quick proof. This is an if and only if statement. So we're going to give two proofs. We're going to give one direction and the other. Let's begin by assuming that the derivative exists. So let's begin the proof over here. So we're going to assume that f prime exists. And then what does that tell us? That tells us that the limit as w approaches z of f of w minus f of z over w minus z is equal to f prime of z. This is the definition of the derivative, of course, but here I'm saying this is a true equation. If this exists, this is a true equation and both sides exist. So now if this is true, then I can subtract f prime of z to both sides. And I'm going to do two steps at once here. The first step is I'm going to subtract it to the other side. And the next step, which is a little bit hard to sort of notice here, is I'm going to, after subtracting it from both sides, I'm going to move it inside the limit so that it's not the limit of the ratio, then afterwards subtract f prime of z. It's the limit of the difference, ratio minus f prime of z. I can do this because this is the limit of as w approaches z. And from the point of view of that limit, this is a constant because it's independent of w. So I can move it inside the limit using the constant law and difference laws for limits. So, okay, now we get a limit of a difference, and we've got a fraction minus a thing, and we're just going to do some basic algebra on this. We're going to make a common denominator. So this will give us the limit as w approaches z of f of w minus f of z minus the quantity w minus z times f prime of z over w minus z. And that's equal to 0. And now what I'd like to do next is I'd like to identify the things that are constant and the things that depend upon w and group them all. Well, I'm gonna sort of rearrange these terms here. So let's look at the limit. Let's change this to the limit as w goes to z of f of w minus, and you know, honestly, I think the best thing to do would be to just write this f prime of z times w minus z plus f of z and put that in parentheses. I think that's the most clear thing to do. So nothing's really happened here algebraically. This term has moved to the front, this term has moved to the back, and I've grouped them together so that I can subtract them as a bundle here. And then that's equal to 0. So these are just very simple algebraic manipulations of the definition of the derivative, but believe it or not, we're already done. Because this is a limit as w approaches z, and this thing is a function of w. It's a function of w, which is of the form w minus the constant z times a constant from the point of view of w, namely the derivative f prime of z, and then plus another constant. So this whole thing here is a linear function of w. Now here, of course, we have f of w, and so we have the difference between f of w and some linear function of w. Now, what are we trying to prove? We're trying to prove that f is L plus G. So in other words, we're trying to show that f minus L equals G. So we've shown that f minus L is equal to something, but what? Well, f minus L is equal to the numerator of this fraction, apparently. And when we take we've also sort of shown that the limit of this numerator divided by w minus z is equal to 0, which is exactly what we want here. So the entire numerator of this fraction is now the function g of w, right? So this function here, this entire thing, is the function g of w. And we have then shown that the limit as w approaches z of g of w over w minus z is equal to 0. There's only one thing left to show, which is that g of z itself is 0. But if we plug in z for w here, then we're just going to get f of z minus f of z plus this thing, which is going to be 0 when w equals z. So g of z is equal to 0 as well. And so this demonstrates that the function f, for the function f, there is a linear function that you can subtract from it, so that the resulting function, the numerator here, divided by w minus z, has a limit of 0 when w approaches z, which is exactly what's claimed here. So the function g is the entire numerator here. So that demonstrates that if f prime exists, then indeed there is a function L and there is a function g, and all of this works as claimed. We need to show the reverse implication. We need to show that if L and G are given and if f is their sum, then the derivative f prime of z exists. And this is actually not hard either. So let's demonstrate that next. So next we're going to assume that L and G are given as described, satisfying all the conditions of the theorem. And we're going to attempt to show that the derivative f prime of z exists. And that's really easy. So if L and G exist as described, then f prime of z is going to be L prime of z plus G prime of z. Now, L prime of z definitely exists. Why? Because L is a linear function, and a linear function always has a defined derivative. So that exists. What about G prime of z? Well, G prime of z, by definition, is the limit as w approaches z of g of w minus g of z over w minus z. Now, what's g of z? G of z is 0. So that's equal to the limit as w approaches z of g of w over w minus z. Is there anything we know about this? Absolutely. That's this limit condition. That limit condition is basically just guaranteeing us that the derivative of g is 0. And so that tells us that's 0. So g prime of z exists and is equal to 0. L prime of z exists, and therefore the sum of those two exists and is equal to the derivative. So thus, f prime of z equals L prime of z. And the important thing here is that the derivative exists. So there we have it. If a function can be approximated by a linear function plus an error function satisfying these conditions, then it's differentiable, and vice versa.